In section 8.3, we're going to be looking at how to test a claim about a proportion. Now, in the last section, we talked about some of the basic pieces of information that are in a hypothesis test, like the critical value, the p-value, the significance level, the null and alternative hypothesis, and how to write a null and alternative hypothesis. Also, we talked about how to find the p-value or find the critical values. So we're going to put all that together to test a claim about a proportion. And this section does present the complete procedures for testing a hypothesis or claim made about a population proportion. And this section uses the components introduced in the previous section for the p-value method, the traditional method, and the use of confidence intervals. Now, we're only going to be dealing with the p-value method and the traditional method when we're dealing with the hypothesis testing in regard to the claim made about a population proportion. All right, now let's look at some of the basic methods of testing claims about a population proportion, which is lowercase p. We'll start with the notation. N is the number of trials, or you can think of this as the sample size. P hat is your sample proportion. And sometimes P hat may be given to you, and sometimes P hat may not be given to you. In that case, you have to calculate that by dividing X, which is the number of successes, by the number of trials, or the number in the particular sample. Okay, so it's always the number of successes divided by the sample size, which will give you your sample proportion, which is p hat. P is the population proportion, and that's used in the null hypothesis. So once you know what p is, Q is going to be 1 minus p. Okay, just subtract whatever that population proportion is from 1 to get what Q is. Q is going to be the number of failures, or the proportion of failures. The requirements for testing the claim about a population proportion would be this. There are 3 of them that you do need to know. One is that the sample observations are a simple random sample. What that means is that each item in that sample has an equal chance of being selected out of that particular sample. Number 2, the conditions for a binomial distribution, which was discussed back in Chapter 5, are satisfied. Okay, and then number 3, the conditions N times P, that's the sample size, times the probability of success is greater than or equal to 5, and N times Q, Q is the probability of failures, is going to be greater than or equal to 5. And they both have to be satisfied, so the binomial distribution of the sample proportions can be approximated by a normal distribution where mu, which is your mean, is equal to N times P, and sigma, which is your standard deviation, is going to be the square root of N times P times Q. And note that P is the assumed population proportion and not the sample proportion, because the sample proportion is indicated by p hat. And this is the test statistic for testing a claim about a population proportion. And in this case here, we use a z-test when we're dealing with a population proportion. So z in this case is going to be equal to p hat minus p. P hat is the sample proportion, and p is the population proportion. So it's going to be p hat minus p, that's divided by the square root of p times q, all divided by n. Okay, and that p times q divided by n is underneath the radical. Okay, now when we're dealing with the p-values, we always use table A-2, which is the standard normal distribution table. And you should already have this table that deals with positive values. Okay, I can't get the table all on here, but pretty much you should already have that table somewhere in your textbook. And also the critical values, you use the standard normal distribution. And also, I did give you a handout that has the common critical z values for testing. So you can use this to come up with your critical Z value when you do the traditional method or use the critical value approach. Do not confuse a p-value with a proportion, which is p. The p-value, by definition, is the probability of getting a test statistic at least as extreme as the one representing the sample data. And the population proportion is just simply lowercase p. Okay, so that's the difference between a p-value and a population proportion. Now, the p-value approach, you use the 8-step hypothesis testing procedure that was provided in the handout. And you should have somewhere in that handout your 8-step method for hypothesis testing. Where in step 1, you're going to state the original claim in symbolic form. Then step number 2, you're going to state the opposite of the original claim, also in symbolic form. Then step number 3, from the first 2 steps, you want to identify the null and the alternative hypothesis. So here, the null hypothesis always has the equal sign, whereas the alternative hypothesis will have either less than, greater than, or not equal to. Then step number 4, you're going to state the level of significance, which is your alpha level. Step number 5 is to calculate the test statistic. And then step number 6, you're going to use either the p-value approach or the traditional method. If you use the p-value approach, you're going to look up the p-value in table A-2. Since we're dealing with a population proportion, in this case, you're going to use table A-2. Then you're going to compare that p-value with the level of significance. Now, if the p-value is less than or equal to alpha, you're going to reject the null hypothesis. Or if the p-value is greater than alpha, you're going to fail to reject the null hypothesis. Okay. Now, the traditional method is using the critical value. So it would be best to draw a normal curve to locate the area of the level of significance, which is your alpha level. And then step number 2, you're going to use that level of significance to find out what that critical value is. And then you're going to compare that critical value with your test statistic. If the test statistic is within that critical region, you're going to reject the null hypothesis. Or if the test statistic is outside the critical region, you're going to fail to reject the null hypothesis. And then step number 7 is to state whether to reject the null or fail to reject the null hypothesis. And then finally, you're going to state the conclusion using simple, non-technical terms to address the original claim. So this is the 8-step procedure for doing a hypothesis test. And you'll be using this throughout section 8-3, 8-4, and 8-5. And the traditional method, as I mentioned earlier, you'll use the 8-step procedure. The only thing that's different is step number 6, where you have to find the test statistic, calculate the test statistic. You're going to do that in step 5. But for the critical region, you're going to use that table of common critical Z values to find out what your critical value is. And then you compare the test statistic to that critical value. So here, if the test statistic lies in the critical region, you reject the null hypothesis. Or if the test statistic does not lie in the critical region, you're going to fail to reject the null hypothesis. Okay. Now, I've already gone over the hypothesis testing procedure that's in your handout. And I've gone over the common critical Z values for your hypothesis testing. Now, I can briefly show you an example. Let's say you have a one-tailed test at the 0.05 level of significance. Using the traditional method, your critical Z value will be 1.645. And then you'll compare that critical value with your test statistic to see if the test statistic is less than or greater than your critical value, depending upon the type of test you have. You can either have a left tail test, a right tail test, or a two-tailed test. let's say you had a two-tailed test at the 0.05 level of significance, then your critical value would be 1.96. And since it's a two-tailed test, that means you'll have negative 1.96 and positive 1.96. And also, this is the slide that deals with the wording of the final conclusion. Here's a better view of that. Now, let's say your claim was the null hypothesis, and you do reject the null hypothesis. Then you'll write your conclusion as this: there is sufficient evidence to reject the claim that such and so and so. Now, if the claim is your null hypothesis, but you fail to reject the null hypothesis, then you'll say that there is not sufficient evidence to reject the claim. And then finish out the sentence. Now, let's say the claim is your alternative hypothesis, which is H1, and you reject the null hypothesis. Then you'll say in your conclusion, there is sufficient evidence to support the claim. Or if you fail to reject the null hypothesis, but your claim is the alternative hypothesis, that means that there is not sufficient evidence to support that claim. Okay? So be familiar with this type of wording of the final conclusion, because in your final statement, you must write this using simple, non-technical terms. Okay, before we get to that, to the examples, let me give you a word of caution. When testing a claim about a population proportion, the traditional method and the p-value method are equivalent and will yield the same result, since they use the same standard deviation based on the claimed proportion, which is lowercase p. However, the confidence interval uses an estimated standard deviation based upon the sample proportion, which is p hat. Consequently, it is possible that the traditional and p-value methods may yield a different conclusion than the confidence interval method. So a good strategy then is to only use the confidence interval to estimate a population proportion. But if you're testing a claim about a proportion, it's best to use the p-value or the traditional method. Okay, so it's best. So in this case, in this video, we're only going to be dealing with the p-value approach and the traditional method when we're testing a claim about a proportion. All right, let's start off with, now on the other handout, you should have example E1. Example E1. In 1997, a survey of 825 households showed 159 of them use email. Use those sample results to test the claim that more than 15% of households use email. And you want to use the 0.05 level of significance, and you're going to use this information to answer the following questions. Which of the following is the hypothesis test to be conducted? Part B, what is the test statistic? Part C, what is the p-value? Part D, what is the conclusion? And part E, is the conclusion valid today? Why or why not? Okay, so here we're going to be using the p-value approach because they asked for the p-value in this case. Okay, now I've already done the hypothesis testing procedure, but I'm going to go through this with you step by step to let you see how this is done. Okay, in step number 1, you have the original claim. Now, in this problem, you're told that you want to test the claim that more than 15% of households use email. So the original claim in this case would be P is greater than 0.15. That's your original claim written in symbolic form, because we're testing the claim that the proportion is greater than 0.15. And 15% as a decimal will be 0.15. Now here's step number 2, stating the opposite of the claim. Now as you can see here, when we state the opposite of the claim, the opposite of greater than will be less than or equal to. So that opposite we use P as the proportion because we're dealing with a proportion anyway. It's going to be less than or equal to 0.15. So the opposite of greater than will be less than or equal to. So the opposite of that claim will be P is less than or equal to 0.15. Now from these two statements in symbolic notation, we're going to write our null and alternative hypothesis. And as you can see here, the original claim has greater than. That has to be the alternative hypothesis because an alternative hypothesis only has greater than or less than or not equal to. So we have to put P is greater than 0.15 under the alternative hypothesis. And that's also the claim, so I wrote down the word claim next to it. The null hypothesis always has the equal sign, regardless of whether you have less than or equal to or greater than or equal to. You always have the equal sign for the null hypothesis. So here P is equal to 0.15 for your null hypothesis. And your alternative will be P is greater than 0.15. And that alternative hypothesis is the claim. And it's best to write this down because when you get to the conclusion, when you're trying to reject the null or failing to reject the null, you want to make sure that that claim is indicated here so that way you'll correctly write down that conclusion. Okay, now I'm going to scoot this down to step number 4, stating the level of significance. And the problem is it does say use the 0.05 significance level. So in this case here, my alpha level is 0.05. And that's all I had to do right here. Just state the level of significance. And by the way, step number 3 was the answer to part A, which is the following hypothesis test is the hypothesis test to be conducted, and this will be it. So part A was already answered. Okay, now step number 5 is going to be the answer to part B, calculating the test statistic. Okay, so let's look at what we have here in this case. We're given a survey of 825 households. That's your N, that's your sample size of 825. We know that 159 use email, so that's what X is equal to, 159. So now we have to calculate what P hat is going to be. Here P hat is going to be X divided by N, which is 159 divided by 825, or 0.193. So P hat in this case will be 0.193. And then we identify what P is. P in this case is from the hypothesized value from your null hypothesis. That's 0.15. So if P is 0.15, Q is going to be 1 minus P, which means we have to do 1 minus 0.15, which will be 0.85. Okay, so that's all the values that we're going to need to calculate our test statistic. And here at the very top is the test statistic. This continues on this side of the paper, which is going to be the answer to part B. What is the test statistic? Here it is. You calculate that by using Z is equal to P hat minus P divided by the square root of PQ divided by N. Okay, so here P hat was 0.193 minus P, which was 0.15. All that's divided by the square root of P, which is 0.15, times Q, which is 0.85, divided by N, which is 825. Okay, now all of this can be typed into the calculator. And in this case here, I'll go ahead and bring up the calculator so that you can see how this is going to be done. All right, in this case here, you need to put the numerator in parentheses. And if you notice, I've already put the parentheses here. That's to let you know that when you do this in the calculator, this needs to be in parentheses. So here we're going to have 0.193 minus 0.15, and then we close the parentheses. Then that's divided by, and then second, x squared for the square root. P is 0.15 times Q, which was 0.85, divided by 825. close parentheses. And then you're going to hit enter. Now, when we're doing a critical z-value, you always round to 2 decimal places. So 3.458918566 to 2 decimal places will be 3.46. So your critical z-value in this case will be 3.46. Okay, so that was step number 5 on your hypothesis testing procedure, and it's also part B of example E1. What is the test statistic, which is 3.46. Now, step number 6 is to calculate the p-value, because we're doing the p-value method in this case, because they want the p-value here. This is where you're going to use table A-2. Okay, so in this case here, I drew the normal curve, label 3.46 here, and it's going to be, now keep in mind, your alternative hypothesis tells you what type of test you're going to have. Here, the alternative hypothesis says greater than. That means that this is a right-tailed test. Notice that I'm finding the area to the right. But table A-2 gives me the area to the left, which means I'm going to have to subtract whatever that area is to the left from 1. Okay, so my test statistic was 3.46 from step number 5. To find that, we're going to find 3.4, which is down here, and then 0.06 is going to be this column right here. Read across is going to be 0.9997. But that represents the area to the left, which is 0.9997. I want the area to the right. Since the area underneath the entire normal curve is 1, let's subtract 0.9997 from 1, which I've done here, and that will give you 0.0003. So my p-value for this situation is 0.0003. Now, step number 7 is determining whether to reject the null or fail to reject the null hypothesis. Here, if the p-value is less than or equal to alpha, you reject the null hypothesis. That's my decision rule here in this case, when we're dealing with the p-value approach. Okay? Now, in this case here, I'm going to compare 0.0003 with 0.05. Compare these two, you can see that 0.0003 is less than 0.05. And because of that, we can reject the null hypothesis. Okay, now we're going to write our final conclusion here. Okay, let me show you how this is done. The claim was the alternative hypothesis, which is H1. And we are rejecting the null, which means we have to start this sentence off, or start the conclusion off by saying there is sufficient evidence to support the claim, which is what I have here. There is sufficient evidence to support the claim that more than 15% of households use email. Okay, so in this case here, this is how we do a hypothesis testing procedure for a proportion. And I do have other examples that I will go over with you. Okay, on your example sheet, look at example E3, where in a recent poll of 755 randomly selected adults, 565 said that it is morally wrong to not report all income on tax returns. Use a 0.05 significance level to test the claim that 70% of adults say that it is morally wrong to not report all income on tax returns. You want to identify the null hypothesis, test statistic, p-value, conclusion about the null hypothesis, and the final conclusion that addresses the original claim. You're going to use the p-value method and then use the normal distribution as an approximation to the binomial distribution. Okay, so here's how this one is set up. Okay, and I'm going to go through each one of these step by step so you can see how this is done. So in this case, step number 1 is stating the original claim. in this case, when we state the original claim, that claim was that 70% of adults say that it is morally wrong to not report all income on taxes. So that's what P is going to be equal to, 0.70. So P equals 0.70. It doesn't say greater than, it doesn't say less than, so we have to say P equals 0.70. That's the original claim. Now, step number 2 is the opposite of the claim. The opposite of equal to will be not equal to. So P is not equal to 0.70. That's the opposite of the claim written in symbolic form. Step number 3. From that, you're going to write your null and your alternative hypothesis. So in this case here, the null has the equal sign in it. So that's P is equal to 0.70, which is also your claim. So I wrote the word claim next to the null hypothesis. Okay? And then the alternative hypothesis has the not equal to. It doesn't have equality, so P is not equal to 0.70. That's your alternative hypothesis. That's step number 3. Just writing the null and the alternative hypothesis. Step number 4 is the level of significance. You were told, in this case, to use a 0.05 significance level. Here it is. That's your alpha level, which is step number 4. Alpha is equal to 0.05. Okay, now step number 5 is calculating the test statistic. In this case here, our N, which is the sample size of 755 randomly selected adults. 565 said that it's morally wrong to not report all income on tax returns, so that's your X, which is 565. So to find out what P hat is, we divide 565 by 755 to get 0.748. So that's what P hat is equal to, 0.748. And then your P is from your null hypothesis, that's 0.70. Which means Q will have to be 1 minus P, or 1 minus 0.70, which is 0.30. And from that, we can go ahead and calculate our test statistic. And this is the formula for the test statistic for a proportion, which is in this case, P hat minus P, all divided by the square root of P hat, P times Q divided by the square, divided by N. All this is under the square root. And then we just substitute our values here. P hat was 0.748, that's this number here, minus P, which is 0.70. All that's divided by the square root of P, which is 0.70, times Q, which is 0.30, divided by 755. And again, this can be typed into the calculator, so I'll go ahead and show you how this is going to be typed in. So here we use our left parentheses for the numerator, which is going to be, and then type in 0.748 minus 0.70, close parentheses, divided by the square root, second square root, 0.70 times 0.30, divided by N, which is 755. And then hit enter. Now, if you get 2.878094608, that's your test statistic, but the 2 decimal point places will be 2.88. So in this case here, 2.88 represents your test statistic. Now you're going to use that in step number 6. That's finding the p-value, because we want to use the p-value method. Okay, so here I drew the normal curve. Now, this is a two-tailed test, and we're using a p-value approach. Back in section 8.2, we talked about how to calculate the p-value when you're given a two-tailed test. That means you have to take 2 times whatever the probability value is for 2.88. Okay, and 2.88 is here, and we're looking for this shaded area to the right. Your table A-2 will give you the area to the left. So in this case here, 2.88 using table A-2 Here's 2.8. 0.08 is over here in this column. And if you read over to the right, you're going to see it's 0.9980. So here, the area to the left here is 0.9980. But we want this area to the right. So 1 minus 0.9980 will give you 0.00220. Okay? But it's a two-tailed test. So we got to do 2 times that area to the right, which is 0.0020, which gives us 0.0040. So that's going to be your p-value. Okay? So only with the two-tailed test, when you're finding the p-value, you got to do 2 times the area that is beyond that particular test statistic. Now, step number 7 is determining whether to fail to reject the null or reject the null. Using this decision rule, if your p-value is less than or equal to alpha, which is your level of significance, you want to reject the null hypothesis. Okay, our p-value was 0.0040. Our significance level back in step number 4 was 0.05. Okay, compare those two, you can see that 0.004 is less than 0.05. So we can reject the null hypothesis because the p-value is less than our level of significance. So we reject the null hypothesis. Now, writing the conclusion. Okay, now let's go back to this right here, avoiding the final conclusion. The null hypothesis was your claim, but we reject the null. So that means we can say that there is sufficient evidence to reject the claim. So in our final statement, using simple non-technical terms, we can write that there is sufficient evidence to reject the claim that 70% of adults say it is morally wrong not to report all income on tax returns. Okay, so that's how we do this hypothesis testing procedure. Okay. All right, let's look at example E6 on your example sheet. Trials in an experiment with a polygraph include 101 results. That includes 26 cases of wrong results and 75 cases of correct results. Use a 0.01 significance level to test the claim that such polygraph results are correct less than 80% of the time. Based on the results, should polygraph test results be promoted as evidence in trials? Here you want to identify the null hypothesis, the alternative hypothesis, test statistic, p-value, conclusion about the null hypothesis, and the final conclusion that addresses the original claim. Use the p-value method and then use the normal distribution as an approximation of the binomial distribution. Okay, so in this case here, I've already got this completed for you, so just pretty much follow along. Okay, we'll start with the original claim. We were told that we want to test the claim that such polygraph results are correct less than 80% of the time. So that's going to be your proportion is less than 0.80. That's the original claim. Then step number 2 is stating the opposite of that original claim. The opposite of less than will be greater than or equal to. So we say P is greater than or equal to 0.80. That's the opposite of the claim. And then step number 3, from steps 1 and 2, you want to state your null and your alternative hypothesis. So in this case here, your null hypothesis will be 0.80 because it has equality in it. The alternative hypothesis will be your original claim. P is less than 0.80. And that's the claim right there that I mentioned there. Step number 4 is stating the level of significance. Here we're using a 0.01 significance level as indicated in the problem. So now your alpha level is 0.01. Step number 5 is to calculate the test statistic. Here, we're told that we have 101 results. That's your n equals 101. Now, we're dealing with 75 correct results. Now, we're not dealing with the 26 because we're testing the claim that such polygraph results are correct. So we want the ones that gave us the correct results in our sample, 75 cases of correct results. That's going to be the x, which is equal to 75. So for p hat, we use x over n, or 75 over 101, and as a decimal, 75 divided by 101 will be 0.743. Your p is from your hypothesized p amount, which is 0.80. That's from the null hypothesis. And q is going to be 1 minus 0.80. That's going to be 0.20. And from that, we can calculate the test statistic. Let me move this over so you can see. Here we got z is equal to p hat minus p divided by the square root of p times q divided by n. P hat was 0.743 minus p, which is 0.80, divided by p, which is the square root of, by the way, p is 0.80 times q, which is 0.20, divided by 101. Again, all of this can be entered into the calculator. So in this case here, you do left parentheses, 0.743 minus 0.80, close parentheses, divided by, and for the square root, second x squared, 0.80 times 0.20, divided by 101. Then hit enter. Now the two decimal places, you're going to have negative 1.43 as your test statistic for z. So negative 1.43 is your test statistic. Now step number 6 is calculating the p-value. Okay, notice here your alternative hypothesis is less than, so that tells me I have a left tail test. So here the p-value is going to be in the left tail. As you can see, I have shaded here. And then negative 1.43 is to the left of 0, by the way. So in this case here, I can just put 0 in the center. And negative 1.43 is to the left of that. So that shaded area is going to be your p-value. Now the table gives us the area to the left, so I'll be okay in finding out what that p-value is, because it is the area to the left. So in this case here, using table A-2, under negative z values, here's negative 1.4, and 0.03 is right here. Go to the right, and that's going to be 0.0764. So 0.0764 is the p-value. Okay. Now I don't need to do 1 minus that because it's already the cumulative area to the left, which is exactly what I wanted here. So 0.0764, that is your p-value. Step number 7 is our decision rule, deciding whether to reject the null or fail to reject the null hypothesis. And here's the decision rule. If your p-value is less than or equal to alpha, reject the null hypothesis. Here's the p-value, which is 0.0764. Our alpha level was from step number 4. That's 0.01. As you can see, 0.0764 is greater than 0.01. It's not less than. So that means we can fail to reject the null hypothesis. And of course, our conclusion, I'll go ahead and pull that back up. The claim was an alternative hypothesis, and we're failing to reject the null hypothesis, which means this statement: there is not sufficient evidence to support the claim. So in this case here, we can say that there is not sufficient evidence to support the claim that the polygraph results are correct less than 80% of the time. Okay, so that's how we state our conclusion using simple non-technical terms. And to answer the question, should the polygraph test results be prohibited as evidence in trials? I would say the answer there would be no. Okay? Because basically, if there's no evidence saying that the polygraph results are correct less than 80% of the time, then that means it must be correct greater than 80% of the time. So in this case here, it should not be thrown out as evidence in trials. Okay. Okay, I got one more example. Now, on this one, we're going to use the traditional method instead of the p-value method, as indicated on your example sheet, because I want you to see how the traditional method works here. In a study of pregnant women and their ability to correctly predict the sex of their baby, 62% of pregnant women had 12 years of education or less, and 41.9% of them correctly predicted the sex of their baby. Use a 0.05 significance level to test the claim that these women have no ability to predict the sex of their baby, and the results are not significantly different from those that would be expected with random guesses. Identify the null hypothesis, the alternative hypothesis, test statistic, critical values, conclusion about the null hypothesis, and the final conclusion that addresses the original claim. Use the traditional method and use the normal distribution as an approximation of the binomial distribution. Okay, so here is that procedure, starting with the original claim. So here is still going to be the same as the p-value method, but step 6 is going to be different. So in step number 1, we state the original claim. Now, don't get this confused here, but in this particular situation, we're trying to test the claim that women have no ability to predict the sex of their baby. The fact is, either they can predict the sex of their baby or they cannot predict the sex of their baby. That's a 50-50 probability. So here, P is going to be 0.5. That's going to be the original claim. Step number 2 is the opposite of the claim. The opposite of equal to will be not equal to. So the probability is not going to be equal to 0.5. Or the proportion that can predict the sex of their baby will not be 0.5. And from that, we can write our null and our alternative hypothesis, which is step number 3. In the null, it has the equal sign, so we use P is equal to 0.5, and that null hypothesis is your claim. Your alternative is going to be P is not equal to 0.5. Okay. Now, step number 4 is the level of significance. In that problem, we're using a 0.05 significance level. So that's your alpha level. Alpha is equal to 0.05. And then step number 5 is calculating the test statistic. Okay. In the problem, it says 41.9% of the women correctly predicted the sex of their baby. So here, that's your P, which is 0.419. That's already given to you. Convert that to a decimal. And if P is 0.5, Q must be 0.5. That's 1 minus P. And your N, which is your sample size, that's the 62 pregnant women who had 12 years of education or less. So N is 62. Now next we calculate our test statistic, which is your Z, equals to P hat minus P, divided by the square root of P times Q all over N. And then P hat was 0.419 minus P, which is 0.5. All that's divided by P times Q, where P is 0.5, Q is 0.5, divided by N, which is 62. Now here we can enter this whole thing in the calculator, so I'll show you how that is done again. I'll clear this out. Left parentheses, 0.419 minus 0.5, and that's closed, all in parentheses, open and closed, then divided by the square root of second x squared, 0.5 times 0.5 divided by 62. Now this one is negative 1.275589276. We round to negative 1.28. Our z-values, we always round to 2 decimal places. So here, the test statistic is going to be negative 1.28. Now, since we're using a traditional method, we want to find out what our critical values are. Okay, so this is what step 6 looks like. Here I drew the normal curve to the best of my ability. Now, the alternative hypothesis is not equal to, which means we have a two-tailed test. That means the alpha level is going to be in both tails, the left and the right tails. Okay, so now we want to find out what our critical value is. Our alpha level is 0.05. Using this common critical z-values for hypothesis testing that's in your handout, you want to look in the column that says level of significance in two tails, and that alpha level is 0.05. Now, if you read to the right of that, you're going to see that critical value is 1.96. Okay? And because it's a two-tailed test, you're going to have two critical values. One's going to be negative, and the other one's going to be the opposite of that. So we have negative 1.96 here, and a positive 1.96 here. Now, the traditional method is this. When we go to step 7, when we write our decision rule, it's going to be this. If your critical z-value, no, not your critical z-value, if your test statistic, which is your z, is less than negative 1.96, because the shaded area to the left is less than negative 1.96. If that test statistic falls within that critical region, if it's less than negative 1.96, or for positive 1.96, anything greater than that will cause us to reject the null hypothesis. So if z is greater than 1.96, if it's one of those two, you're going to reject the null. Otherwise, you're going to fail to reject the null. So think of this. To the right, if it's to the right, you're going to reject the null. If it's to the left, you're going to reject the null. If it's in between those two critical values, you're going to fail to reject the null. Okay? So now, our test statistic was negative 1.28 from step number 5. Negative 1.28 falls within these two boundaries, negative 1.96 and positive 1.96. It's not greater than 1.96, and it's not less than negative 1.96. So here, we're going to fail to reject the null hypothesis. Okay? Now, to write our conclusion, let's go back to this. The null hypothesis was our claim. We failed to reject the null hypothesis. So that means that there is not sufficient evidence to reject the claim. So when we write our conclusion, it's going to be this. There is not sufficient evidence to reject the claim that pregnant women have no ability to predict the sex of their baby. Okay, that's the conclusion there. And this is how we use the traditional method to conduct a hypothesis testing for a proportion. Okay. So in this video, we've already discussed how to do test statistics for a claim about a proportion. And also we did the p-value method, and also we used the traditional method as well on one of the problems. Okay, so do look at the answers to your example sheet on Campus Cruiser. Also, good luck with your homework, and do feel free to watch this video as much as you need to, and also feel free to ask me any questions or send me email if you have problems. Okay?